All right, today we are diving into, well, one of the most fundamental and, honestly, one of the coolest concepts in all of physics. We're talking about entropy. You know, it's this hidden rule that's running the show for everything, from your coffee getting cold all the way to, yeah, the ultimate fate of the entire universe. So let me ask you this. Have you ever really thought about it? You pour a hot cup of coffee, you put it on your desk, and what happens? It cools down every single time. But have you ever seen a lukewarm coffee just spontaneously start heating up on its own? No way, right? So what's going on? Why does everything in the universe seem to be stuck on a one-way street? And believe it or not, the answer isn't just about coffee. It's about everything. It's why an egg can fall and smash into a million pieces, but you'll never see those pieces magically jump back together. It's why your room gets messy all by itself, but never ever tidies itself up. It's even why we remember what happened yesterday, but have no idea what's going to happen tomorrow. It all comes back to this one single powerful idea: entropy. So this really gets us to a much bigger, kind of universal puzzle, which is the direction of time itself. And here's the weird part. If you zoom all the way down to a single atom or particle, the laws of physics, they don't really care. They work perfectly fine going forward in time or backward in time. It makes no difference. And yet for us, in our world, time obviously has a direction, right? It's an arrow always pointing from the past straight into the future. I mean, just think about it. You build a perfect sandcastle, and the tide comes and washes it away. A nice, neat stack of papers on your desk, a little breeze, and boom, they're everywhere. It's this constant, relentless march from order into, well, chaos. We see it absolutely everywhere. And that tendency, that's exactly what we're going to unpack today. Okay, so to really get our heads around this arrow of time, we've got to zoom in. I mean, way in. We need to look at the universe through the eyes of the genius physicist who first started to put all these pieces together. And his name was Ludwig Boltzmann. Now, Boltzmann, he was a total visionary. He put forward this idea that the big things we can feel and measure, like temperature or pressure, aren't fundamental things on their own. Nope. He said they're just the result of what trillions and trillions of tiny, jiggling atoms are all doing together. I mean, that was a wild idea back then. So radical, in fact, that it's kind of sad, but his work wasn't really appreciated until after he was gone. So, his big idea, the core of it all, was something called a microstate. Okay, so picture this. Think about all the little molecules of air in the room you're in right now. A microstate is like a snapshot, one very specific arrangement of where every single one of those molecules is and how fast it's going. The key thing to realize is that there are just a staggering number of ways those molecules could be arranged. And some of those arrangements are just way, way, way more likely to happen than others. And Boltzmann, being the genius he was, boiled this whole idea down into one of the most important equations in all of physics. It looks simple, right? S equals kb times the natural log of omega. So S here, that's our entropy. That omega symbol, that's the total number of all those possible microstates we just talked about. And kb is just a number that makes the math work, a constant. This beautiful little formula is the bridge. It connects the big macroscopic world of entropy with the tiny microscopic world of pure probability. And you want to know how important this equation was to him, to his entire life's work? It is literally carved on his tombstone. I mean, just think about that. It's such a powerful tribute to an idea that people argued against in his lifetime, but is now just fundamental to how we understand the entire cosmos. All right, so we've had a look at Boltzmann's microscopic world, this world of probabilities and atoms. Now let's zoom back out. Let's see how all of that tiny stuff actually shows up in the big macroscopic world that we all live in and experience every day. So what is entropy in simple terms? It's really just a measure of disorder or randomness. That's it. It's the reason your coffee cools down. The heat energy spreading out into the room is a much more disordered and therefore a much more probable arrangement for that energy. At the end of the day, the universe just prefers to move toward states that have more disorder, more entropy. Now, here's a really important detail about entropy. It's what scientists call a state function. So what on earth does that mean? Well, think of it like this. Let's say you're taking a trip from New York to LA. You could fly direct, or you could take a winding road trip through 10 different states. It doesn't matter how you get there, your starting point was New York and your ending point was LA. Your change in position is the same either way. Entropy is just like that. The change in disorder only cares about the start state and the end state, not the crazy path you took to get from one to the other. So you see, these two views, the microscopic and the macroscopic, they're not different things. They're just two sides of the exact same coin. Boltzmann's world of probabilities, with all those microstates, it perfectly explains the world of disorder that we see around us. When you have more possible arrangements for all the little particles, that just translates to more messiness, more disorder on the big scale. And that is the direction that nature is always, always heading. Okay, I get it. This can all still feel a little bit out there, kind of abstract. So let's bring it down to earth. Let's make it totally concrete. Can we actually put a number on this increase in disorder? You bet we can. Let's do a quick calculation for a super simple process, boiling a pot of water. So the formula for this looks pretty simple. The change in entropy, which we call delta S, is just the amount of heat you add, that's delta H, divided by the temperature, T. And we have to use Kelvin for the temperature. For water, we know these numbers. The heat it takes to turn it into steam is 40.7 kilojoules for every mole, and it boils at 373 Kelvin. So all we have to do is plug those numbers right into the formula. And, drumroll please, what do we get? We get 109.11 joules per Kelvin mole. Now, the number itself isn't the important part. What's crucial is that it's a positive number. That positive sign is the proof. It confirms that entropy, disorder, went up. And that makes total sense, right? A cloud of steam with molecules zipping all over the place is way more disordered than a calm puddle of liquid water. Okay, so we've gone on quite a journey here, right? From a cup of coffee down to individual atoms and back up to boiling water. So why should you care? Why does all this matter? Well, because this one concept, entropy, it gives us the answer to one of the biggest, deepest mysteries there is, the arrow of time. Just think about this for a second. The past is a state of lower entropy. It was more ordered. It happened. We can remember it. But the future is a state of high entropy. It's a vast sea of possibilities, of disorder, which is why we can't know what's going to happen. This constant, unstoppable, irreversible increase of entropy across the whole universe, that is the physical process that draws the line between yesterday and tomorrow. It's like the engine of time itself, always pulling it forward. And so, all of this leaves us with one last really big question to chew on. If the entire universe is constantly and without exception moving towards a state of maximum disorder, maximum entropy, what does that mean for its ultimate end? What is the fate of everything? Something to think about. Thanks so much for joining me.